This is the third part of a four-part lecture on proprioception. And in this part, we're going to cover three more proprioceptors: the Golgi tendon organ, joint kinesthetic receptors, and the vestibular apparatus. So far, we've learned about the mechanoreceptors in our skin and the muscle spindle that's in our muscles. Both of those send signals when certain kinds of things happen. When you press on your skin, the mechanoreceptors signal. When you stretch certain muscles, the muscle spindle signals. So let's talk about the Golgi tendon organ. I have a picture up on the right-hand side that shows a bicep muscle and a tendon that goes from the bicep muscle and attaches to one of the bones in your forearm. So whenever you do a bicep curl, you contract your bicep muscle and it pulls on the tendon, right, and on the bone and raises your hand up. So whenever you contract your muscles, you essentially move your bones, you move your body. But to be able to move your body, you have to put tension on a tendon that's attached to a bone. And so that's the Golgi tendon organ. The Golgi tendon organ is a receptor that is in the tendon that's in between the bone and the muscle. So surely there's a proprioceptor that helps me understand the amount of force that I'm producing when I contract my muscles. And indeed, we do have one. It's called the Golgi tendon organ. When does it fire or signal? Well, when a muscle contracts and pulls on a tendon, then the Golgi tendon organ fires. And the amount of Golgi tendon organs that fire, or the intensity of their firing, is in relation to the amount of force that's being exerted. So whenever you have a 5-pound dumbbell in one hand and a 20-pound dumbbell in the other hand, and you do curls in the hand with only 5 pounds of weight, the Golgi tendon organ is signaling like this: ding, 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 ding. But in the hand that's got the 20-pound dumbbell, it sounds like this: ding, 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 ding. So the frequency of the signal, the intensity of the signal, is in relation to the amount of force that's being pulled on the tendon. So what do we believe that the Golgi tendon organ helps us do? Well, the Golgi tendon organ really tells us about not necessarily the tension in our muscles, but the forces that we are producing using our muscles. So the Golgi tendon organ is very much responsible for helping us produce the right amount of force. So whenever you want to hold an egg in one hand and a 20-pound weight in the other hand, you have to squeeze hard with one hand and light with the other hand, and the Golgi tendon organ helps us produce the right amount of forces. The second thing that the Golgi tendon organ helps us do, or we believe helps us do, is coordinate our muscle contractions. So whenever we do an activity, and I have a person doing some dumbbell overhead presses in the picture on the bottom. Now when you do this exercise, when you raise the weight up, you have to contract certain muscles, and you will have to relax other ones. And you have to do that for every exercise, but we'll use this as an example. To do an overhead press with a dumbbell, you have to contract the muscles in your shoulder, in your deltoid, and you also have to contract the muscles in your tricep so that you can straighten your arm. So those are the two primary movers, so those muscles need to contract. Now, to be able to push that arm up over our head, we have to relax other muscles that are called the antagonist muscles, the muscles that prevent you from moving or would go in the opposite direction. So in this case, you need to relax your bicep, and you also have to relax the muscles in your back, your lats, so that you can press the weight up over your head. So you have to contract certain muscles and relax other ones. And the Golgi tendon organ, we believe, helps our brain and neuromotor system coordinate the muscle contractions. So while the Golgi tendon organ is not inside the muscle, the Golgi tendon organ detects forces that are on the body and that the body is producing, and helps us produce the right amount of force. Now, if we have receptors in our muscles and in our tendons, then we probably also have some receptors that are within and around our joints that tells us about our joint position, and indeed we do, and they are called joint kinesthetic receptors. Now, joint kinesthetic receptors are both within and around the joints. So you have some nerves that, for example, might go from your spinal cord down your arm, towards your shoulder, and then they end all around the shoulder joint. And they attach to those joint kinesthetic receptors. And so what do the joint kinesthetic receptors detect, or when do they fire? Well, they're activated primarily whenever we move a joint. We move it fast, or we put it in one of the extreme limits of position or rotation, or when there's a lot of force that's being exerted on the joint. So I have a picture here of a baseball pitcher. Whenever I see this kind of a picture, it always makes me cringe a little bit because it looks like that would hurt, because the shoulder joint is rotated way behind, right? Way behind their body. So whenever a baseball pitcher is doing this activity, the joint kinesthetic receptors in the shoulder are very activated because we have basically stretched that joint to an extreme limit of its range of motion, and it's going to move really, really fast. The other thing that the joint kinesthetic receptors senses is whenever we have a lot of pressure or force on a joint. So whenever you are lifting weights, if you lay down on your back on the bench press machine and you grab hold of the bar and there's like 100 or 150 pounds on the bar, and there's a lot of pressure down on your shoulder joints, then your joint kinesthetic receptors in your shoulders would be activated. So the joint kinesthetic receptor, it's in and around the joint. It signals whenever that joint moves or is put in an unusual position or an extreme limit of its range of motion. Signals from the joint kinesthetic receptors, we believe, helps us understand, again, our position and movement of our limbs and body parts. That joint position sense. Is my arm over my head? Is it down by my side? Is it behind me? Is it in front of me? And the joint kinesthetic receptor helps us understand this position, particularly of our limbs. And it also signals a lot whenever, again, we get into some kind of an unusual position or an extreme range of motion around the joint that helps us respond, to tighten up those muscles to prevent some injuries. So the muscle spindle, and the joint kinesthetic receptor, and the Golgi tendon organ are sometimes what's called mechanical inputs because they're all part of the musculoskeletal system. The last two proprioceptors are a little bit different and a little bit weird. This one is called the vestibular apparatus. And so my metaphor for the vestibular apparatus is a bottle of liquid. And so you see a picture of it down there. So I just want you to imagine for a minute that you are riding in a car and you're holding this bottle of liquid and you're watching the liquid move around in the bottle. And so when the car would begin to move forward or accelerate, the liquid in the bottle would move. When the car accelerated forward, then basically the water or the liquid would move backward in the bottle. It would rise up on the back of the bottle and it would dip down in the front of the bottle. And then whenever your person would put on the brakes, the water would do just the opposite. It would slide forward and ride up on the front of the bottle, and then the edge of the liquid would be low on the back of the bottle. So the liquid would move around the edge of the bottle as you accelerate, as you speed up or as you slow down. Similarly, if you went around a corner, then you would see that the liquid would again slide to the outside of the glass and dip down on the inside while you were cornering, while you were turning. And then whenever you got back to a straight part of the road, the liquid would flatten out. So the vestibular apparatus is kind of like that. It's kind of like a bottle of liquid. Where is the vestibular apparatus located? Well, it's inside your head, right? It's in your inner ear. And I have a picture of some of the structure of the vestibular apparatus, and the most significant feature is the cochlea, right? That thing that looks kind of like a snail shell. And again, there's a bunch of liquid, fluid in the cochlea that moves around with you. When does the vestibular apparatus activate, or when is it more likely to signal? Well, it signals whenever you change direction or you change the speed of your motion, when you accelerate or decelerate. So if you are standing still and you lean forward, the vestibular apparatus, the water in your bottle, begins to move around in the bottle. As you lean forward, as you lean backward, as you bend over to the right, as you bend over to the left. The water, the liquid in the bottle would slide around, and you could watch it and you could tell some things about the positioning of your head or the position of your body when you balance, when you just stand up straight. Also, when you accelerate, and I have a picture of a sprinter, when you are accelerating, speeding up, or when you are slowing down, the vestibular apparatus signals, the water slides around, and it tells your body that about the rate of acceleration. Basically, it tells you you're speeding up or you're slowing down. So, what is the information used for? When the vestibular apparatus begins to signal, what does it tell your brain? Or what does your brain have to figure out? Well, when you're not in motion, it tells you information about your head position. And again, your head is attached to your body, and so the vestibular apparatus is extremely important in you maintaining your balance. If you lean over, vestibular apparatus tells you you're leaned over. When you straighten up, the vestibular apparatus tells you you are in balance. So it tells you a lot about your balance. The second thing the vestibular apparatus does is it tells us about relative motion. It tells us about acceleration, deceleration, spinning around of our body. So we use the vestibular apparatus, when we're standing still or sitting down in a chair. It tells us it helps us with our balance. And whenever we move around, it tells us about our relative speed. Are we speeding up or are we slowing down? Weird, but extremely important.